Light bends when gravity pulls. The first great illusion in space shows us that mass can twist the path of a photon. We watch this bend like a hidden lens. In 1915, Einstein wrote field equations that tied geometry to matter. The equations said that any mass, no matter how small, reshapes the surrounding fabric. I find it hard to picture a fabric that is not cloth but a four-dimensional stretch of space and time. When a star sits between us and a distant source, its gravity pulls on passing photons. The photons do not travel straight, they curve ever so slightly. The amount of curvature depends on the star's mass and its distance from the light path. Einstein himself calculated the deflection for light grazing the sun's edge. He predicted an angle of about 1.75 arcseconds, tiny, but measurable with a good telescope. The prediction felt almost absurd at first, as if the sun could act like a tiny glass bead. In 1919, Sir Arthur Eddington organized an expedition to the island of Principe. He aimed his lenses at the sun during a total eclipse, hoping the sun's glare would disappear. When the plates were developed, the positions of background stars shifted exactly as Einstein had said. It didn't quite make sense when you say it aloud. A massive ball of fire bending the sky behind it. That single experiment turned a theoretical curiosity into an observational fact. It also opened a door to a new kind of astronomy, one that relies on the bending of light rather than its own glow. We began to treat gravity as a natural telescope. Imagine a galaxy cluster, a massive collection of hundreds of galaxies, dark matter, hot gas. Its combined weight can bend light from galaxies far behind it. The light paths are stretched into arcs that arc across the sky like faint rainbows. Those arcs are called gravitational arcs, and they appear in deep images of massive clusters. Sometimes the alignment is almost perfect. The source, the lens, and the observer line up on a single axis. The light then forms a complete circle around the lens, an Einstein ring. The ring's radius tells us directly the amount of mass inside the lensing region. Measuring that radius is like reading a ruler drawn in light. Even when the alignment is imperfect, the source can be split into multiple images. A single quasar may appear as 2 or 4 points of light around a foreground galaxy. Those points flicker in unison because they are the same object, just seen along different routes. The time delay between flickers can be measured, offering a way to estimate the Hubble constant. The magnification effect is perhaps the most practical outcome. A distant galaxy that would otherwise be invisible can be brightened by a factor of 10 or more. The lens acts like a natural telescope, letting us peer farther back in time. In some cases, we see galaxies as they were when the universe was a fraction of its current age. Modern surveys, such as the Sloan Digital Sky Survey and the Dark Energy Survey, scan the sky for these lensing signatures. Automated algorithms flag arcs and rings for human inspection. The sheer volume of data now dwarfs what Eddington could ever have imagined, yet the basic principle remains the same. Mass bends light. One must be careful, however, not to mistake intrinsic galaxy shapes for lensing arcs. A spiral galaxy seen edge-on can look like a thin line, but it lacks the curvature that lensing imposes. Careful modeling of the lens mass distribution helps separate the two. We still refine those models. The field is not closed. The mathematics behind the bending is straightforward in principle. Light follows a null geodesic, the straightest possible path in curved spacetime. The curvature is encoded in the metric tensor, a set of numbers that describe distances locally. Solving the geodesic equation for a given mass distribution yields the deflection angle. In practice, we often use the thin lens approximation, treating the mass as if it were confined to a single plane. This simplifies calculations without losing essential accuracy for most astronomical lenses. The approximation feels like flattening a mountain into a ridge. The ridge still blocks the view, but the problem becomes manageable. Observationally, we measure the positions, shapes, and brightnesses of the lensed images. From those, we reconstruct the projected mass map of the lens. The map reveals not only visible matter, but also the invisible dark matter that dominates the cluster's gravity. In a sense, lensing lets us feel the weight of what we cannot see. There are limits, of course. If the source lies too far from the line of sight, the deflection is too small to detect. If the lens is too low in mass, the arcs remain below the resolution of our instruments. We don't really know how many faint lenses hide in the data, waiting for better telescopes. Future facilities like the Vera-C Rubin Observatory will increase our sensitivity to subtle lensing signals. The observatory's wide field will capture more clusters, more arcs, more rings, yet the core idea stays unchanged. Gravity reshapes the path of photons, and we read that reshaping as an illusion. Even now, a single Hubble image of the galaxy cluster Abell 2218 shows dozens of faint arcs curling around bright galaxies. The arcs are thin, ghostly, and slightly blurred, as if a hand had brushed a piece of paper. That blur is the telescope's point spread function, not the lens itself. When we stare at those arcs, we are looking at light that has traveled billions of years, bent by an invisible hand. The hand is the mass of the cluster, a mixture of stars, gas, and dark matter. The light has been delayed, stretched, and amplified before reaching our eyes. One striking example is the Einstein cross, a quasar whose light is split into 4 images around a foreground galaxy. The 4 points form a cross-shaped pattern, each image separated by about 1 arcsecond. The pattern is stable, yet the brightness of each point can vary over months, reflecting the light's different travel times. Those variations teach us about the lens's geometry. By measuring the delay, we infer the distance to the lens and the source. The technique provides an independent check on cosmological parameters. It feels like listening to a clock tick from 2 different rooms and deducing the wall thickness. Gravitational lensing also reveals substructures within lenses. Small clumps of dark matter can perturb the arcs, creating tiny wiggles. Detecting those wiggles requires high-resolution imaging and careful modeling. The effort shows that even the smallest mass concentrations leave a trace on the light. In the laboratory, we cannot replicate such massive curvature. The strongest fields we can generate bend light by fractions of a nanoradian, far below astronomical scales. That limitation reminds us how unique the universe is as a natural laboratory. We must rely on observation, not experiment, for many of these effects. The illusion of a bent sky also reminds us that straight is a local concept. A photon traveling through empty space follows a path that is locally straight, yet globally curved by mass. The notion of a universal straight line loses meaning when spacetime itself is flexible. Sometimes I stare at a distant galaxy whose image is stretched into a thin arc and wonder how many other galaxies are hidden behind it, magnified but not yet recognized. The arc itself is a thin line of light, a reminder of the unseen mass that shaped it. A final note: the first great illusion of the universe, gravitational lensing, continues to teach us about mass, geometry, and time. It forces us to accept that what we see is not always where the source truly lies. In a quiet night, a faint ring may appear around a distant galaxy, its light looping once, twice, perhaps more, before reaching us. The ring's edge is sharper on one side, a subtle brightening where the lens's mass density peaks. The mass of a galaxy cluster hangs in space like a heavy slab of steel, bending the fabric of space-time around it. Light that passes near this slab does not travel straight. It is nudged, stretched, sometimes split into several copies. When the alignment is just right, the cluster works as a natural telescope, magnifying objects that would otherwise be invisible. In the strongest part of the field, what we call the strong lensing regime, the distortion is dramatic. A single distant galaxy can appear as a quartet of arcs arranged around the cluster core, each arc tracing a different path through the warped geometry. The classic Einstein cross is a tiny example of this effect, only on a galactic scale. In clusters, the same principle produces giant luminous arcs that stretch for tens of arcseconds across the sky. I find it hard to picture how a single source can be seen in 4 places at once, but the math of general relativity forces that conclusion. Just outside the region of extreme bending lies the weak lensing regime. Here the background galaxies are not torn into arcs. Instead, their shapes are subtly stretched, their ellipticities aligned with the cluster's mass distribution. By measuring these tiny shape changes across thousands of galaxies, we can infer the projected mass map of the whole cluster. The signal is faint, often a few % change in axis ratio, but with enough galaxies the pattern emerges like a fingerprint. The fingerprint tells us more than the visible galaxies. Most of the mass that produces the lensing does not emit light. It is the elusive dark matter that forms a scaffold for the cluster. By comparing the locations of the bright galaxies with the lens-derived mass map, we see that dark matter extends far beyond the luminous core, filling the space between galaxies like an invisible glue. We don't really know what this glue is made of, but the lensing data give us the only direct way to see its shape. The Hubble Space Telescope took advantage of this effect in the Frontier Fields program. 6 massive clusters were observed for hundreds of orbits, each image revealing dozens of new background galaxies, some magnified 100-fold. One of the fields showed a faint galaxy at redshift 9, its light stretched into a thin, bright ribbon that would have been undetectable without the cluster's lens. The program turned the clusters into a network of magnifying glasses, allowing us to peer back to the first few 100 million years after the Big Bang. These deep images also sharpened our view of the dark matter distribution. By feeding the observed arcs and weak lensing shear into sophisticated inversion algorithms, astronomers reconstructed 3-dimensional mass models of the clusters. The models show clumps of dark matter that line up with the brightest cluster galaxies, but also reveal massive substructures that have no luminous counterpart. Such dark clumps are a reminder that our picture of the universe is still incomplete. Strong lensing also offers a route to measuring cosmic expansion. The time it takes light to travel along different paths around a cluster is not identical. The multiple images of a variable source, such as a supernova, arrive at slightly different moments. If we can record the delay between the images and know the geometry of the lens, we can infer the Hubble constant, the rate at which space itself stretches. A recent supernova behind a cluster produced 3 images separated by weeks. The measured delays matched predictions only when a particular value of the Hubble constant was used. It doesn't quite make sense when you say it aloud, how a distant explosion can whisper the expansion rate of the whole universe, but the mathematics holds. The method is not without pitfalls. Small errors in the mass model translate directly into errors in the inferred distance scale. Weak lensing measurements can be contaminated by intrinsic alignments of background galaxies, and strong lensing models can suffer from degeneracies where different mass configurations produce similar image patterns. Researchers therefore combine multiple lenses, cross-check with independent distance indicators, and iterate their models until the residuals shrink to an acceptable level. It feels a bit like tuning a radio. You turn the knob, listen for static, adjust again. Even with these challenges, cluster lenses remain one of the few tools that let us map dark matter directly. Alternative techniques, such as galaxy rotation curves or the cosmic microwave background, probe different scales or epochs, but they cannot resolve the fine structure within a single massive halo. The lensing maps from the frontier fields show dark matter filaments weaving through the cluster, intersecting at nodes that correspond to the brightest galaxies. In a way, the clusters act like a laboratory where gravity, light, and unseen mass interact in a tangible form. When we look at a lensed arc, we are also looking at a time-delayed view of the source. The light that forms the outermost arc left the galaxy earlier than the light that makes the inner arc, because the outer path is longer. The time differences can be millions of years, a span that dwarfs human history. It is a humbling reminder that the images we capture are not snapshots of a single moment, but stitched together fragments from different ages. The ability to measure the Hubble constant with lenses adds a new piece to a puzzle that has been growing louder in recent years. Different methods, supernovae, the cosmic microwave background, baryon acoustic oscillations, have yielded slightly discordant values. Cluster lensing offers an independent check that does not rely on the same assumptions as the other techniques. If the discrepancy persists, it may hint at new physics beyond the standard model, perhaps an alteration in dark energy or an unknown particle species. We are not there yet, but the lensing data are already nudging the debate. In practice, constructing a reliable lens model starts with cataloging every visible arc and every faint galaxy whose shape can be measured. Software packages fit a parametric mass distribution, often a combination of smooth halos and smaller clumps, to reproduce the observed image positions. The model is refined iteratively, each step reducing the offset between predicted and actual image locations. When the residuals fall below a few tenths of an arcsecond, the model is considered robust enough for scientific use. The process feels methodical, almost mechanical, yet each cluster presents its own quirks that keep the work from becoming routine. One of the most striking results from the frontier fields was the discovery of a galaxy whose star-forming regions were stretched into a line of bright beads, each bead representing a star forming not magnified by a factor of 50. Without the cluster's lens, we would have missed the knot entirely. The observation gave us a glimpse of how early galaxies assembled, hinting that star formation could be highly clumpy in the infant universe. The lens turned a distant speck into a detailed map, a feat that would have required a telescope many kilometers in diameter otherwise. The same principle applies when we try to count the total mass of a cluster. By adding up the mass inferred from lensing with the mass measured from X-ray emission of the hot intracluster gas, we can test the assumption that dark matter dominates the gravitational potential. In most cases, the two measurements agree within uncertainties, reinforcing the view that dark matter is the primary scaffold. Occasionally, they diverge, suggesting that the gas is not in perfect equilibrium or that the lens model missed a substructure. Those outliers keep the field honest. Looking ahead, the next generation of space telescopes will push the lensing technique even further. Wider fields of view and deeper exposures will capture more background galaxies, sharpening the weak lensing signal. At the same time, adaptive optics on ground-based observatories will resolve finer details in strong lensing arcs, allowing us to map dark matter on scales of a few thousand light-years. The combination promises a more complete picture of how mass assembles in the universe. Yet even as the instruments improve, the fundamental limitation remains. We can only infer mass from how it bends light. If dark matter interacts with itself or with ordinary matter in ways we have not imagined, the lensing signal could hide subtle effects. We may never know whether the smooth halos we reconstruct are truly smooth or merely an average over unseen granularity. The data give us a map, but the terrain beyond the map stays hidden. In the quiet moments after a night of data reduction, I sometimes stare at a single stretched arc and wonder about the galaxy that produced it. Its light has traveled billions of years, been tugged and split by a massive cluster, and finally landed on a detector that records a faint line of photons. The arc sits there, a thin, bright ribbon against the dark sky, a reminder that gravity can act as both a magnifier and a mirror. The edge of the arc is sharper on one side, a tiny kink where a dark clump nudged the light path just enough to create a corner. That kink, barely perceptible, is the only clue we have to a piece of invisible mass. The microwave background we observe today is a thin veil of photons that escaped when the universe was about 300,000 years old. At that moment, the hot plasma of electrons and protons finally cooled enough for atoms to form, and photons stopped scattering. The surface where this happened is called the last scattering surface, a spherical screen that surrounds every observer, a snapshot frozen in time. When we point a telescope at any direction, we are really looking at a tiny patch of that screen, a region a few 100,000 light-years across. The temperature we measure is not uniform. It varies by a few parts in 100,000. Those variations are the illusion we call anisotropy, but they are not tricks of our instruments. They are the imprint of sound waves that rippled through the primordial plasma. In the early soup, gravity tried to pull matter together while radiation pressure pushed it apart. The competition set up standing acoustic waves, much like the resonances of a drumhead. Where the compression peaks were strongest, the plasma was slightly hotter. Where the rarefactions lay, it was cooler. When the photons finally decoupled, those temperature differences were frozen into the last scattering surface. The pattern we now map is a fossil record of those ancient oscillations. The power spectrum of the anisotropies shows a series of peaks, acoustic peaks, each corresponding to a mode that had just the right phase when decoupling occurred. The first peak marks regions that completed half an oscillation, the second a full oscillation, and so on. Their positions tell us how far sound could travel before the plasma turned transparent, which in turn depends on the density of ordinary matter and the amount of dark matter. It is a subtle measurement, but the peaks line up with the predictions of a simple model, and that alignment is why we trust the picture. Temperature variations also arise from a gravitational redshift known as the Sachs-Wolf effect. Photons climbing out of a potential well lose energy, appearing cooler. Those falling into a well gain energy, appearing warmer. This effect operates on the largest angular scales, where the acoustic pattern is washed out. It adds a gentle tilt to the map, a reminder that geometry and gravity still shape the light long after the plasma vanished. One region, however, stubbornly resists easy explanation. The cold spot, a roughly 5-degree patch that is colder than surrounding areas by about 20 microkelvin, stands out in the otherwise random field. Some analyses suggest it could be a statistical fluke, others propose a supervoid, a vast underdensity that stretches across hundreds of millions of light-years, altering the photon energy via the integrated Sachs-Wolf effect. Still, we do not really know. I find it hard to picture how a single void could produce such a clean, circular dip, and the data do not settle the matter. Polarization adds another layer of subtlety. As photons last scattered, the local quadrupole of the radiation field imprinted a faint linear polarization on the outgoing light. This polarization pattern comes in two flavors: E modes, which are curl-free, and B modes, which carry a swirling component. The E mode map aligns with the temperature anisotropies, confirming that they share a common origin in the same acoustic oscillations. Detecting B modes would hint at something else, perhaps primordial gravitational waves from an inflationary burst, yet the signal remains elusive. The current limits tell us that any such waves must be weaker than a few % of the total energy budget at that epoch. The data we collect are not pictures in the ordinary sense. They are statistical fields. Each pixel on a map is a random draw from a probability distribution set by the physics of the early universe. When we average over many modes, the underlying pattern emerges, but any single realization, our sky, contains quirks. That is why the cold spot feels like an illusion, a glitch in an otherwise smooth statistical fabric. Even the notion of a temperature for the microwave background is a bit of a shorthand. The spectrum is an almost perfect black body, described by a single temperature of 2.725 Kelvin, yet the tiny fluctuations we speak of are deviations from that mean. In practice, we measure intensity differences at specific frequencies, convert them to temperature units, and then map them onto the sky. The conversion assumes a linear response that is accurate only because the variations are so small. It doesn't quite make sense when you say it aloud, that a handful of photons can encode the entire history of the first 300,000 years. The last scattering surface is not a physical wall but a statistical horizon. Photons that we receive today have traveled for 13.5 billion years, stretched by the expansion of space. Their wavelengths have been redshifted into the microwave band, and the original temperature fluctuations have been diluted, yet the pattern remains. It is as if a faint imprint on a piece of glass has been stretched until the glass itself is invisible, leaving only the pattern of light. When we look at the polarization vectors, we see tiny arrows that trace the direction of the electric field. Their alignment changes across the sky, forming a delicate web that mirrors the acoustic peaks. In regions where the temperature is a hot spot, the polarization vectors tend to radiate outward. In cold spots, they converge. The correlation is subtle, but it is measurable, and it reinforces the idea that the same sound waves set both temperature and polarization. The precision of modern instruments allows us to resolve anisotropies down to a few arcminutes. That resolution is equivalent to spotting a grain of sand on a beach from a kilometer away. Yet even with that level of detail, we remain limited by foregrounds: dust emission from our own galaxy, synchrotron radiation, and the faint glow of distant galaxies. Removing those contaminants is a careful exercise, a sort of lab note where each correction is logged and its impact on the final map recorded. The process reminds us that what we call the microwave background is never observed in isolation. It is always filtered through layers of later structure. One lingering question is the exact shape of the power spectrum at the smallest scales. Damping, known as silk damping, smooths out fluctuations below a certain size because photons diffuse out of overdense regions before decoupling. The resulting tail of the spectrum falls off, but the precise rate depends on the ionization history and the number of light particle species. We can infer the presence of 3 neutrino families from that damping, yet the exact contribution of any extra relativistic particles remains uncertain. We don't really know whether a hidden particle could be hiding in that tail, barely nudging the curve. In the end, the microwave background is a vast, faint mirage, a relic of a time when the universe was a hot, dense plasma, its motions frozen into a pattern we can still read. The temperature map, the acoustic peaks, the Sachs-Wolf tilt, the cold spot, and the faint polarization together form a delicate illusion that tells us more about the early state than any direct observation could. As we refine our measurements, the picture sharpens, but the fundamental paradox remains. We are looking at a surface that never existed as a solid object, only as a momentary release of photons. If you stare long enough at a patch of the sky near the cold spot, you can see the polarization vectors twist ever so slightly, a fraction of a degree, as if the ancient sound wave left a whisper in the orientation of the electric field. The light that grazes a neutron star feels the pull of a weight far beyond Earth's gravity. It bends, stretches, then snaps back toward us, sometimes completing a half-orbit before escaping. I note the way the path curves like a tight rope under tension. At a distance of about 1.5 times the Schwarzschild radius, photons find a precarious balance. In that thin shell called the photon sphere, they can circle endlessly if nothing disturbs them. I find it hard to picture a beam looping forever, yet the equations leave no room for doubt. If a photon slips just inside that sphere, the pull becomes fatal. The trajectory spirals inward and the light disappears behind an invisible edge. The edge is what we later call the shadow, a dark silhouette against the surrounding glow. A black hole's shadow is not a solid object. It is a region where no light can escape. The Event Horizon Telescope captured that silhouette in a faint ring of emission. The ring's thickness tells us how tightly space is warped near the horizon. The ring itself is not uniform. Parts of it shine brighter, others dimmer. That unevenness comes from relativistic beaming. Light emitted from material moving toward us is compressed, appearing brighter. Light from material receding is stretched, appearing fainter. I write this down as a simple cause and effect, though the math behind it is anything but simple. The material responsible for the bright ring is an accretion disk, a whirl of gas and dust spiraling inward. As the gas speeds up, its temperature rises and it glows in X-rays. Those carry the imprint of the space they have traversed. One imprint appears as an iron K alpha line, shifted from its laboratory wavelength. In a calm laboratory, iron emits at 6.4 keV. Near a black hole, the same line spreads from lower to higher energies, forming a broad, skewed profile. I call this iron line spectroscopy a probe of the warped spacetime. The low-energy wing of the line tells us how much the photons have been pulled outward, gravitational redshift. The high-energy wing records how much they have been pushed forward, Doppler boosting. Together, they map the motion and depth of the gravitational well. Gravitational redshift also affects any photon climbing out of a neutron star's field. A photon emitted at the surface loses energy, its wavelength stretching as it climbs. The effect is small compared to a black hole, but measurable with precise instruments. Time itself slows near these compact objects. A clock ticking at the surface of a neutron star runs slower than a distant clock. I cannot directly hear that slowdown, but the spectral lines shift in a way that betrays the slower passage of time. When a photon skirts a neutron star, its path bends just enough to create a secondary image of the star's far side. The star appears doubled, with one image slightly displaced. I have seen simulations of that effect. The two spots sit a few micro-arcseconds apart, far beyond the reach of most telescopes. If the neutron star spins rapidly, its surface drags spacetime along, a phenomenon called frame dragging. Photons that travel with the spin find an easier path. Those against it are forced into tighter curves. The net result is a subtle asymmetry in the observed light pattern. In the case of a black hole with a bright accretion disk, the inner edge of the disk sits close to the innermost stable circular orbit. Inside that radius, matter plunges straight in, leaving a dark gap. The gap's size depends on the black hole's spin. Faster spin pushes the gap inward. I have tried to sketch that gap in my notebook, marking the bright ring, the dark shadow, and the faint glow beyond. The faint glow comes from photons that have looped around the black hole once or twice before escaping. Those photons arrive later, their paths longer, their energies altered. Those looping photons form a photon ring, a narrow, bright line hugging the shadow's edge. The ring's brightness is a fraction of the total emission, but its existence confirms that light can orbit a black hole at least once before breaking free. I admit I find it hard to imagine a photon completing a full circle around a region where nothing can escape. The photon ring's thickness depends on how many orbits the photons survive before scattering. In an ideal vacuum, the ring would be razor thin. In realistic environments, scattering broadens it. The Event Horizon Telescope's data hint at a faint, extended component beyond the primary ring. Neutron stars, though smaller, also produce a faint halo of scattered light. Their magnetic fields channel particles into hot spots which emit X-rays. Those can be bent around the star, creating a secondary hot spot image that arrives later. The delay is a few milliseconds, a tiny but measurable interval. The delay offers a way to test the star's mass and radius. By measuring the time difference between the primary and secondary pulses, we infer how much space is curved. I have written down the formula, but the practical uncertainties keep the result fuzzy. When the neutron star spins, the hot spots sweep across our line of sight, producing a pulsating signal. The pulse shape is altered by gravitational light bending. The far side spot becomes partially visible. This effect smooths the pulse, making it less sharp than a simple rotating beacon would suggest. In some binary systems, a neutron star or black hole accretes matter from a companion star. The inflow creates bright X-ray flares that flicker on timescales of seconds. Those flares illuminate the surrounding material, producing reflected spectra that carry the imprint of the warped spacetime. The reflected spectra often show the same iron line, now broadened by both the motion of the reflecting material and the gravitational field. By fitting the line shape, we can extract the inclination of the disk, the spin of the black hole, and the degree of redshift. It feels like a forensic analysis of light. Even the simplest observation, a single photon arriving from a distant black hole, carries a story. Its energy tells us how deep the gravity well was, its direction hints at the bending it endured, its arrival time records any loops it may have taken. I try to keep that perspective when I look at raw data. The instruments that capture these photons are delicate. They must operate at cryogenic temperatures, shielded from Earth's atmosphere and calibrated to sub-% precision. Any systematic error can masquerade as a physical effect, leading us astray. I note that caution repeatedly in my lab notebook. Sometimes the data refuse to match the simplest models. The iron line may appear more extended than predicted, or the shadow may look slightly asymmetric. Those mismatches could hint at new physics, or they could be artifacts of the observing process. I remain skeptical, waiting for independent confirmation. In the end, the visual phenomena around neutron stars and black holes are a blend of geometry, motion, and extreme gravity. They remind us that light is not a straight line in these neighborhoods. It is a flexible messenger, bent, stretched, and sometimes trapped. I keep the picture of a photon looping once twice before slipping away. A final note. The Event Horizon Telescope's image of the black hole shadow shows a bright crescent on the left, a dimmer side on the right. That asymmetry reflects the direction of the disk's rotation relative to us. I can't help but stare at that crescent, wondering how many photons have taken the longer, winding route to reach our detectors. The instruments we point at the night sky act like extensions of our own eyes, yet they do more than simply magnify distant points of light. They rearrange the very way we can register a flicker of a distant star, a bend in a background galaxy, a ripple in spacetime. In that rearrangement, the illusion of emptiness turns into a map of hidden structure, and the map still contains gaps we cannot fill. Interferometry is the first step beyond a single telescope's reach. By linking dishes across continents, we stitch together a virtual aperture the size of a continent. The result is an image that resolves details finer than a human hair seen from a kilometer away. I have watched a radio interferometer resolve the inner ring of a distant accretion disk, a thin glow that would have been smeared into a blur by any solitary dish. The data arrive as a pattern of phase differences, a kind of mathematical grain that we translate into a picture. It feels like we are listening to the sky with a stethoscope, feeling the pulse of matter that we cannot see directly. Space-based observatories add another layer. A telescope orbiting far from Earth's atmosphere can catch the fleeting brightening of a background galaxy when a massive object passes in front, a gravitational lensing event. The lens acts like a glass sphere, but on scales of billions of kilometers. The brightening is a brief, sharp spike in the light curve, a signal that we can record only because the instrument stays in a stable thermal environment, free from the turbulence that would smear the image. When the lensing peak fades, the data remain as a record of a moment when space itself bent the path of photons. Gravitational wave detectors bring a different sense altogether. Instead of seeing, we now hear. The detectors are massive interferometers that measure changes smaller than a proton's width as a wave passes through Earth. The first detection felt like a faint tap on a drum, a sound we had only theorized about. Each new event adds a note to a growing composition of the universe's violent mergers. The instruments translate a stretch of spacetime into a time series plot, a line that rises and falls like a breath. I find it hard to picture how a ripple in the fabric of reality can be rendered as an audible chirp on a screen, but the translation works. Artificial intelligence now helps us turn those raw measurements into visual forms. A neural network trained on simulated data can fill in gaps where our telescopes have no coverage, producing reconstructions of hidden structures, filaments of dark matter, the interiors of supernova remnants. The AI does not invent, it interpolates based on patterns it has learned. Yet the output still feels like a painting, a suggestion of what might be there. I sometimes stare at an AI-generated map of a galaxy cluster and wonder whether the smooth gradients are truly present or merely the algorithm's best guess. It doesn't quite make sense when you say it aloud. We are seeing what we have not measured. These extensions of perception raise questions that linger beyond the data. When we turn illusion into insight, we also confront the limits of what can be known. A lensing event tells us the mass distribution along a line of sight, but it cannot tell us the composition of that mass without additional clues. A gravitational wave signal reveals the masses and spins of merging black holes, yet it tells us nothing about the environment that surrounded them before the merger. The AI reconstructions give us a plausible picture, but the underlying physics remains partially hidden. We don't really know whether the patterns we see are the only possible configurations or just one of many that fit the data. Future missions promise to stretch these senses even further. A proposed space interferometer would place multiple collector mirrors tens of kilometers apart, forming an aperture that could resolve the event horizon of a nearby black hole directly. A next-generation gravitational wave observatory on the far side of the Moon would be shielded from terrestrial noise, catching lower frequency waves from supermassive black hole mergers. An array of small, autonomous satellites could swarm around a lensing event, sampling the light curve from many angles at once. Each of these ideas feels like a step toward turning more of the invisible into the visible, yet each also adds a new layer of uncertainty about how the instruments themselves shape what we observe. Philosophically, the act of seeing the unseen reshapes our notion of reality. When a telescope records a photon that has traveled billions of years, the image is not a snapshot of a present moment. It is a record of a past that no longer exists. Interferometric images blend light that left different parts of a source at slightly different times, stitching together a composite that never existed as a single object. Gravitational wave detections capture a fleeting distortion that disappears as quickly as a breath. The AI-generated visuals are, in a sense, a conversation between human expectation and mathematical inference. The more we extend our senses, the more we are reminded that what we call reality is always filtered through a chain of instruments, models, and assumptions. There is a quiet fatigue that settles in after weeks of calibrating a detector, watching the data streams, and wrestling with systematic errors. The numbers can feel as heavy as a slab of lead, the plots as cold as metal. Yet the occasional moment when a faint signal rises above the noise, when a lensing curve peaks, when a chirp appears, carries a weight that steadies the mind. In those moments, the illusion of emptiness recedes, replaced by a concrete pattern that we can trace, measure, and discuss. Even as we build ever more sophisticated tools, some aspects remain stubbornly out of reach. Dark matter, for instance, continues to reveal itself only through its gravitational influence, never through emitted light. The interiors of supernovae explode in a flash that our detectors can catch only in the afterglow, leaving the core processes shrouded. The AI can suggest a filament's shape, but without independent verification, the suggestion stays provisional. I find myself repeatedly returning to the same thought. Every instrument opens a new window, yet the wall behind the window is still there. The last thing I notice before turning off the console is a faint, persistent hum in the cooling system of the interferometer. It is a low, steady vibration that reminds me that even our most precise measurements sit on a foundation of ordinary physical noise. The hum is not part of the data we seek, but it is part of the reality we live in. It lingers, a small, unremarkable vibration that persists long after the signal has faded.